Okay, so in this video we're going to move on in the textbook, in the IB Physics textbook. This is going to be under 3.2. We're going to start talking more about ideal gases and behavior of gases. We saw in the first video in this unit the difference between a solid, liquid, and a gas. And in a gas, the atoms or molecules making up the object are basically they're all separated from each other and they're all moving freely for each other. And this is what we call the microscopic picture. By microscopic picture, I mean looking at things on a really tiny scale, okay, as opposed to the macroscopic scale, which is more like human size that we can see with our eyes. The microscopic view is more kind of like fine-tuned, looking at what's happening with individual atoms or molecules. Okay, now in that first video we talked about, temperature is the average kinetic energy of the particles making up an object. We also talked about the pressure of a gas. The pressure of a gas, as we saw in that first video, is related to the frequency of collisions that the particles of the gas make with their container. And so, in this unit, or in this section of the unit, we're going to be kind of more generalizing the behavior of some types of gases, which we call ideal gases. And so we're going to spend a few days talking about that. So, first, we're going to do a quick recap of the microscopic view of pressure, and then we're going to talk about pressure in a more macroscopic way, like a more big picture, human size scale type of way. So first, let's do a brief review over the microscopic view of pressure. So, if you go to this slide, we talked about before how temperature is a measure of the average kinetic energy of the atoms or molecules making up an object, and that's true whether it's a solid, liquid, or a gas. If the temperature of a gas increases, so does the average speed, and therefore the average kinetic energy of the molecules, because remember, kinetic energy is just energy of motion. So the faster the particles making up the object are moving, the higher the temperature. Now, it is important that you understand that that all objects are made of atoms or molecules or whatever. And there's a lot of them, okay? There's a ton of atoms in any given object. Like, we're not talking millions or billions, we're talking like trillions of trillions, okay? We'll talk about Avogadro's number later just so you can appreciate how many we're talking about. It is important that you understand that if you have an object at a set temperature, not all of the atoms or molecules have the exact same temperature, okay? In fact, the temperature, there's like a distribution called the Maxwell-Boltzmann distribution that basically shows you how some atoms might be moving slow, some might be moving fast. That's why we use the word average when we're talking about temperature. Okay, so it's not that every single if we increase the temperature of something, it's not that the temperature of every single atom will increase, but on average the atoms will increase in temperature. Okay, so here we can see in this animation the difference between high, medium, and low temperature. Okay, so moving on to talk about pressure and how that relates to pressure. We talked before about how for a gas, the pressure has to do with the frequency of collisions with the container walls. Okay, now that is the microscopic view of pressure, by the way. In a few minutes we'll talk about the macroscopic view of pressure. But we can clearly see there's some type of relationship between temperature and pressure. Now, they're not the same thing, right? They measure two different quantities. But clearly we can see that if the size of the container is fixed, if the particles are moving faster, that is, if they have a higher temperature, they're going to collide more often. And therefore, the pressure is going to increase. Okay, so there is some type of positive correlation between pressure and temperature of a gas. Okay, now temperature is not the only factor that affects pressure. Okay, you can also imagine if you had, let's say, 3 different containers with particles at the same temperature, meaning the same average kinetic energy, that they would behave differently. Now, you might look at this and be like, oh, the one on the left is moving faster. Well, it's not really moving faster. It's just that the container is smaller, and so it looks like it's moving faster. You can see on the thermometers that they all have the same temperature, and so on average, the particles making up this gas would have the same kinetic energy and therefore the same speed. However, because the container on the left is so small, you have more collisions happening per second than you do in the other 2 containers. Okay. And so clearly we can see that there is another factor that affects pressure, and that is volume. Okay, so for a gas, the pressure is going to be bigger if the volume is smaller. I know this word is cut off here at the bottom, but that word is smaller. The pressure will be bigger if the volume is smaller. Okay. And so now we're going to kind of shift to more of the macroscopic view of pressure. Okay, looking at, what does pressure actually mean on a big human-sized scale? Because we can't see individual atoms or molecules. We can't see them colliding with their container walls. Okay, so we're going to kind of transition to the macroscopic view of pressure now. Okay, so imagine a gas molecule confined in a closed box as shown. Because the molecule is changing direction, that means its momentum is changing every time it changes direction. And if there is a change in momentum, there must be a force, there must be an impulse acting. Okay, in other words, every time the gas particle changes direction, there has to be some type of force acting. Now, where is this force coming from? It's coming from the walls of the box, right? Every time the particle collides with the container walls, there's a force on the particle that makes it change its direction, right? And so that's where that force is coming from. Okay, because of Newton's third law, if there's a force from the box on the gas particle, there must be a force from the gas particle on the walls of the box. Okay, and so the walls of the box feel that force. Okay, we would say that they feel a pressure P given by the formula below. Okay, and so this is the macroscopic understanding of pressure. Okay, this is the big person understanding of pressure. We have P equals F over A. And really this should be a capital P. I'm going to rewrite it up here. P equals F over A. Okay, pressure, that's a big P, not to be confused with power or momentum. Okay, this is pressure. Pressure is the force per area. Basically, when you exert a force divided by a certain area. And so in this case, the force we're talking about would be the force on the walls of the box from the gas particles inside the box. Okay, and the area would be the area of the box itself. Okay, now the reason I said this is a macroscopic understanding of pressure is because we can measure force directly. We can measure area directly. All this talk about, frequency of collisions is all, well and good, but we can't actually see those things directly measure those things. Okay, so there's a difference between the microscopic understanding of pressure of a gas, which has to do with how often those collisions happen, versus the macroscopic understanding, which has to do with things that we can measure as humans, like force and area. So we're going to do some calculations with this equation here in a second. You should be able to see from the equation, though, that pressure, okay, if it's force over area, the units of this would have to be newtons, that's the unit for force, divided by the unit of area, which in the SI system would be meters squared. Okay, so newtons per meter squared. Now, we don't call it newtons per meter squared. Yeah, I mean, I guess we could. We call it PA, and that stands for Pascal. Okay, so that is the SI unit for pressure. Okay, so pause it there if you need to add that to your notes. Okay, so going on to the next slide, we're going to do some examples with pressure. Okay, so it says a 50-kilogram man stands on 1 foot on some ice. Given that his foot is only about 9 centimeters by 10 centimeters in a rectangular cross-section, find the pressure on the ice. Okay, so pressure is a force spread out over an area. Now you might ask, what is the force here? Well, the force, if you think about what force is the man exerting on the ice, that is just the force of gravity. That is just Fg. And we can calculate the force of gravity for the man, at least the magnitude, which is all we care about. I should tell you actually right off the bat that pressure is a scalar. It does not have direction. Okay, so really we only care about magnitudes in this equation. The force of gravity for the man, assuming that we use g equals 10 meters per second squared for the acceleration to gravity, would be about 1500 newtons. Okay, that is the force that the man standing on the ice exerts. Okay, now he's standing on 1 foot, and it tells us in the problem to assume that his foot is like a rectangle, which is kind of weird, 9 centimeters by 10 centimeters. Now, A is the area of his foot, but that's supposed to be in square meters, remember. So the area of a rectangle is length times width, but we actually need to convert that to meters before we do any calculations. So that would be 0.09 times 0.10. Okay, and that would be 0.009 square meters. Okay, so we have his force, which is his weight, and it's spread out over the surface area of his foot, which is 0.009 square meters. We can easily do this calculation and see what pressure he is exerting on the ice. So I'm just going to type that into my calculator, and I get a pressure of about 166,666.7. And remember, the unit for that is pascals. Now, it's very common to see another unit of pressure, just because these numbers tend to be so big, and that is kilopascals. Okay, and so you could also write this as 166.7 kPa, where kPa is kilopascals. You might have seen kPa sometimes on pressure gauges for your car tires or your bike tires. But that is a unit of pressure. Other units of pressure, by the way, that you might be familiar with would be like PSI, pounds per square inch. Okay, pounds is a unit of force, not the SI unit of force, but pounds is a unit of force, and square inch is a unit of area. Okay, so if you ever hear about PSI, pounds per square inch, that is another unit of pressure. Okay, again, not the SI unit of pressure, but a unit of pressure. Okay, so that is a simple calculation with pressure. Alright, so I'm going to clear that off. Okay, here you can see the full answer. They ran it up to 170,000 pascals. That's probably just to keep the correct number of sig figs. There should be 2 sig figs in this problem. I'm not going to worry too much about sig figs though. The next problem is just another example where it says if the ice is thin enough that it will break under a pressure of 1 times 10 to the 5 pascals, what should the area of a snowshoe that will just prevent him from breaking through when on 1 foot? Okay, so similar problem. We still have the same force, that is the force of gravity, which is 1500 newtons, but now we want to spread it out over an area. Remember, pressure is force over area. We want to spread it out over an area so that the pressure is less than this value. Okay, so really we need 1.5 times 10 to the 5. We need that to be the maximum value. So we need F over A to be less than or equal to this value here, right? Because otherwise the ice is going to break. So we want to find A such that this inequality is true. So A should be, do I have this right? Yes, I believe so. Okay, so that means A should be greater or equal to 1500 over 1.0 times 10 to the 5. So the area of the snowshoe, if you've ever seen a snowshoe, or if you haven't, you can Google what a snowshoe looks like. Basically, the purpose of the snowshoe is to increase the area of your foot, because the idea is if you take your weight and you spread it out over a bigger area, it's going to decrease the pressure, and so the ice is not going to break. Okay, so we find that the area has to be greater than or equal to 0.015 square meters. Okay, now if it's less than that value, then his force is not going to be spread out enough, and the pressure is going to cause the ice to break. Okay, so that's another simple example with the pressure equation. And again, this is a macroscopic understanding of pressure, right? Because these are like real world, like life-size situations that we can analyze. We're not talking about like atoms colliding with anything here, right? We're talking about things we can physically measure, like force and area. Okay, so I'm going to go to the next slide. This slide is just talking about the difference between microscopic versus macroscopic. Again, the microscopic view is, having to do with the collision of the particles, whereas on the macroscopic level, we're talking about force being applied per unit area. Okay, so make sure you understand the difference between the microscopic and the macroscopic view. Now, they can relate to each other. For example, we'll do one more example. It says an ideal gas is placed in a container which has a movable piston as shown to the right. The gas is at STP. You don't need to know what that means, but that means standard temperature and pressure with a pressure of 101.3 kilopascals. kPa is kilopascals, and the piston has a cross-sectional area of 14 square centimeters. Pay attention to the units, by the way, because area should be measured in SI units. It should be in square meters. We're going to have to convert that. Calculate the force that is required to hold the piston in position to stop it from expanding. Okay, now the microscopic view has to do with how often the gas particles collide with the piston. But remember, every time the gas particles collide, they put a little bit of force on the piston. Okay, this is the piston here. Okay, so there's bajillions of gas particles all bouncing off of the walls, bouncing off of this piston, hitting it, wanting to push it up. In order to stop the piston from going up, we have to apply a force down, and so that has to do with the pressure of the gas. And so this problem kind of like connects the microscopic view with the macroscopic view of pressure. The microscopic viewpoint has to do with how often the gas particles collide, whereas the macroscopic viewpoint has to do with the force per unit area exerted on the piston by the gas. Okay, so we want to find the force that is required to stop the piston from expanding. Okay, so remember, pressure is force per area. Okay, so the force we have to apply down on the pistons to stop it from expanding has to at least equal the force, or it has to be equal to the force exerted up on the piston. Now again, why is there a force up on the piston? Because these gas particles are running into the piston from below. They're going pow, 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 pow. Okay, billions of times per second. Okay, so that means there's a force up on the piston, and we have to apply a force down to stop it from expanding. So we are given that the pressure is 101.3 kPa. In SI units, that would be 101.3 times 10 to the 3 pascals. I write 10 to the 3 because remember kilo is 10 to the 3. And then the area is 14 square centimeters. Okay, now to go to square meters, which we have to do, right? It's been a while since we did this type of calculation. But the way you set this conversion up is you start with, okay, 14 square centimeters. I have to have square centimeters on the bottom. I know that there is 100 centimeters in 1 meter. But wait, I need centimeters squared. And so I need to square the bottom, and then I square the top. And so I'm actually doing 14 divided by 100 squared. Okay, and 14 divided by 100 squared is 0.0014 square meters. Okay, so make sure you understand how to do those types of conversions. Remember, it's a little bit different when you have a unit being squared. Okay, so besides that, this is a very basic type of problem. We're looking for F. F would be P times A, so 101.3 times 10 to the 3 times A, which is 0.0014. Okay, and so the force that we have to apply to kind of withstand all of these gas collisions, I'm just going to type this into my calculator, is 141.8 newtons. Okay, so this is the answer to my question. Again, a very basic type of calculation, but understand that the origin of the pressure of this gas comes from those particle collisions, right? That's the microscopic viewpoint. The macroscopic viewpoint has to do with, oh wait, we have to apply a force to stop this thing from expanding. Now, what if we heat up the container? Then those gas particles move faster. That means they collide with more force, which means we would have to apply a greater force to stop the piston from expanding, which means that the pressure would increase. Okay, so all these things kind of relate to each other. That is the macroscopic understanding of pressure. Pause it here if you need to. Okay, so the last few slides we're going to talk about today is the kinetic theory of gases. Okay, now there's a few facts you need to know. Please add the slide into your notes. Okay, but just to go over some of these things briefly, the internal energy of an ideal gas consists only of kinetic energy. Okay, that is a key fact that you must know. Now, this is only true for an ideal gas. Now, remember that internal energy, by definition, is the internal potential energy of the particles, the atoms or molecules, plus the internal kinetic energy of those particles. Okay, now I'm telling you for an ideal gas, there is no internal potential energy. Okay, that's one of the characteristics of an ideal gas. An ideal gas, the atoms or molecules making up an ideal gas do not have any potential energy between them. Okay, now in a real gases there is internal potential energy because in a real gas you're not ignoring the electrical forces between the gas particles, but you do in an ideal gas. Okay, so we're going to assume that the potential energy part of the internal energy is 0 for an ideal gas. Okay, now we're going to make some other assumptions that we're going to go based off of. This one I talked about before. Molecules in a real gas experience interactions between one another due to electrical forces. Therefore, they have internal potential energy. Again, this is for a real gas. Real gases have internal potential energy and internal kinetic energy. Ideal gases only have internal kinetic energy. Now, what is the difference between an ideal gas and a real gas? In other words, when can you approximate a real gas as an ideal gas? Because there's no such thing as a real perfect ideal gas, but there's a lot of gases that we can pretend are ideal gases as long as they meet certain criteria. So we can treat a real gas as an ideal gas as long as it has a low pressure, low temperature, a low pressure and density, and a moderate temperature. And the reason for that is the key assumption that we're making is that the gas particles do not have any electrical forces between them. Now, that is only true if the gas particles are far apart from each other. If the gas particles are far apart from each other, right? Let me write this down. This is only true if gas particles are spread out. You can only ignore the electrical forces and therefore the potential energy because of those forces if the gas particles are spread out. So what does that mean if they're spread out? That means they're not very dense. That means there's not a lot of pressure. That typically means low to moderate temperature because the faster they move, the closer they are together in general. And that typically also means relatively higher volume. Okay, so again, an ideal gas can be approximated an ideal gas can be a good approximation for real gas as long as it meets those criteria. But really, again, these three things all come down to this, okay? Because you can only treat a real gas as an ideal gas if you're in a situation where you're more or less free to ignore those electrical forces between the gas particles, right? Now, I spent a lot of time talking about when can a real gas behave as an ideal gas. And the reason is we're going to talk about some of the properties of ideal gases. And ideal gases, it's much easier to solve problems with ideal gases because of the assumptions that we're going to make. Okay, now there's lots of situations where a real gas cannot be treated as an ideal gas. Typically, you only see those types of problems if you take chemistry at the college level. The nice thing about ideal gases is that they make some what could be complicated problems a lot simpler because the equations having to do with ideal gases are much easier to deal with. Okay, so pause it here if you need to. And then the next slide is just talking about some of the properties of an ideal gas. Please make sure that you add these to your notes. Okay, an ideal gas is an imaginary gas that is used to model real gases and has the following properties. Again, you need to know what these are and be able to describe the properties of an ideal gas. Okay, now this is not the same thing as the difference between an ideal gas and a real gas. Okay, these are just the properties of an ideal gas. Okay, so we are assuming that the molecules that make up an ideal gas are identical perfect spheres, that they are perfectly elastic. Remember, an elastic collision from the last unit is a collision where kinetic energy is conserved. So we're assuming that the particles of an ideal gas don't lose kinetic energy when they collide with each other, that there's no intermolecular forces. Of course, we know that this is one of the key differences between an ideal gas and a real gas. There's no electrical forces between the gas particles. That is, they have no internal potential energy, and that they're so small that their volume is much smaller than the volume of the container. Those are just some of the assumptions we're making about ideal gases. Okay, so I believe that is it. We are going to move on to something slightly different, but we're still going to be talking about ideal gases in the next video. So please let me know if you have any questions. After the next video, you should be able to work on your next worksheet.